Assalamu alaikum. Myself Zahida Azmat. I am from BS Chemistry department. Today my presentation topic is electrochemical nitrogen cycle. So without wasting our time, let's start the presentation. Here a key diagram of nitrogen cycle in which we see the NO3, NO2, NH4 and NH3 are converted into atmospheric N2. We explain all these processes like nitrification, assimilation, denitrification, and nitrogen fixation for the formation of nitrogen gas. These are the outlines of my presentation, which includes the introduction, basics of electrochemical conversion, key chemical pathways like electrochemical nitrogen reduction reactions, electrochemical nitrification, electrochemical denitrification, material and catalyst design, electrolytes and cell design, applications, advantages of electrochemical nitrogen cycling, challenges and limitations. At the end, we see the research trends of electrochemical nitrogen cycle, future prospects, and then we conclude it. First of all, we introduce it. Definition of the nitrogen cycle. The nitrogen cycle is the natural process through which nitrogen moves between the atmosphere, soil, water, and living organisms. It includes nitrogen fixation, nitrification, assimilation, ammonification, and denitrification. First of all, we understand the natural processes. All these processes which happens automatically in the atmosphere is called natural processes, which includes photosynthesis, respiration, decomposition, weathering, and erosion. The second term in this paragraph is nitrogen fixation. Nitrogen fixation is a process where nitrogen from the atmosphere is converted into usable form for living organisms, typically through lightning strikes, certain bacteria, and industrial processes. The second term is the nitrification. Nitrification is the two-step process where ammonia is converted into nitrites and then nitrates by specific bacteria. Assimilation is the process by which plants, animals, and microorganisms convert nutrients into their own biomass, like plant absorbing nitrates and animals consuming plants and using nutrients for growth. Ammonification is the process where organic matter like dead plants and animals is broken down by decomposers, releasing ammonia back into the environment. Denitrification is the process where certain bacteria like Pseudomonas convert nitrates back into the nitrogen gas, releasing it into the atmosphere. This completes the nitrogen cycle. Now we will saw the details or importance of the nitrogen for life like proteins, DNA and fertilizer. Nitrogen is a key element in amino acids, building block of the proteins and nucleic acid, DNA and RNA. Plants need nitrogen to grow, so containing fertilizers are essential for agriculture and food production. Here is the main question: how nitrogen is the key element in amino acids and nucleic acid. Nitrogen is a fundamental component of amino acids and nucleic acids. Nitrogen is part of the amino group NH2 in amino acids, which are the building block of protein. Nitrogen is a key part of the nitrogenous base adenine, guanine, cytosine, thymine and uracil in DNA and RNA. The second one is the nitrogen containing fertilizers. Some common nitrogen containing fertilizers like urea, ammonium nitrate, ammonium sulfate, and calcium ammonium nitrate. After this, we discuss the limitations of the natural nitrogen fixation. Natural nitrogen fixation by lightning and nitrogen fixing bacteria is slow and not enough to support global agricultural demand. Atmospheric nitrogen is very stable and difficult to convert into usable forms. The main question here is why nitrogen fixation by lightning and nitrogen fixing bacteria is slow. Nitrogen fixation by lightning and fixing bacteria is considered slow because lightning it is an intermittent and energy intensive process happening only during thunderstorms. And due to nitrogen fixing bacteria, they are limited in numbers and often require specific conditions like legume roots. The second one is the why fixation by lightning and nitrogen fixing bacteria is slow and not support agricultural demand. The, it is not enough to meet the agricultural demand due to limited frequency, limiting capacity, and high demand. Third one is the usable forms of atmospheric nitrogen includes nitrate, ammonia, and nitrites. Now we will discuss the need for electrochemical approaches like clean, efficient, and sustainable. Electrochemical nitrogen conversion systems use electricity, preferably from renewable sources, to convert nitrogen into useful forms or useful compounds like ammonia. These methods operate at low temperature and pressure, reduce carbon emission, and provides a more sustainable alternative to traditional industrial processes like the Haber-Bosch process. Why? Why there is a need of electricity for the electrochemical nitrogen conversion? Because we want to break the strong N triple bond N in atmospheric nitrogen, and second one we convert the N2 into more reactive forms like ammonia and nitrates. Haber-Bosch process is an industrial method that produces ammonia from nitrogen and hydrogen gases. It requires high pressure and high temperature, pressure like 150 to 300 atm and temperature like 400 to 500 degrees Celsius. And it uses the catalyst iron. Here is the main question how nitrogen is converted into ammonia. In the Haber-Bosch process, nitrogen is converted into ammonia through nitrogen fixation, high pressure and temperature, and by using iron catalyst. Now we will discuss the basics of electrochemical nitrogen conversion. The first one is role of electricity to drive the nitrogen relating reactions. Electrochemical nitrogen conversion uses electrical energy to break the strong triple bonded nitrogen molecules, convert them into useful compounds like ammonia or nitrates. Electricity provides the electrons needed for reduction or oxidation reactions, making the process more controlled and efficient, especially when powered by renewable sources like solar or wind energy. How electricity by renewable sources making the process more efficient by using electricity from renewable sources like solar, wind or hydropower can make nitrogen fixation more efficient by powering electrochemical process, enabling decentralized production, reducing carbon footprint and increasing energy efficiency. The second one is the use of catalyst and electrolytes. Catalysts help absorb and activate nitrogen molecules, making them more reactive. Different materials such as metals, metal carbides, nitrides, and single atom catalysts are used to improve the reaction speed and selectivity. How catalyst activates the nitrogen molecule in the Haber-Bosch process? The iron catalyst weakens the strongest N triple bond N, absorb N2 molecules, reducing bond energy, facilitates the hydrogen addition, forming ammonia. Electrolytes acidic, neutral, or alkaline solution provide ions that participate in the reaction and help carry charge within the electrochemical cell. But how it is possible the electrolyte provides ions in the electrochemical cell? In the electrochemical cell, electrolytes provides ion by dissociating into ions like proton, hydroxide, Na plus or Cl minus, and facilitating the ionic conduction. Third option is the enabling redox reaction at electrodes. Common electrolytes includes aqueous solution like water and salts, or solid materials includes membranes and ceramics. Ambient and high temperature systems. Electrochemical nitrogen conversion can occur under. The first one is the ambient condition, the second one is the higher temperature systems. Room temperature and atmospheric pressure making the process energy efficient and suitable for distributed small scale setups. But what is the mean by the conversion of nitrogen under ambient condition? The conversion of nitrogen under ambient conditions refer to the process of fixing nitrogen into more reactive forms like ammonia and nitrates at low temperature or room temperature atmospheric pressure without extreme energy inputs. High temperature systems like solid oxides electrochemical cells which operate at several hundred degrees Celsius and allows faster reactions rates but require more energy and complex material. The conversion of nitrogen at high temperature system refers to the processes that fix nitrogen into more reactive forms at elevated temperatures, typically in Haber-Bosch process 400 to 500 degrees Celsius, often combined with high pressure, for breaking the strongest and triple bond and enabling the conversion into ammonia or other nitrogen compounds. Now here is a comparison with the traditional industrial process Haber-Bosch. The Haber-Bosch process converts nitrogen and hydrogen into ammonia using high temperatures and high pressures. It is energy intensive and relies heavily on fossils. In contrast, electrochemical method operates at low temperature and pressure, produce fewer carbon emission and can be powered by renewable electricity. Although still developing, they offer a more sustainable and modular alternatives. The Haber-Bosch process actually requires high temperature, high pressure to proceed efficiently. Lower temperatures and pressures would result in slower reaction rates and lower yields, making the process less efficient. That's why Haber-Bosch process is proceeds at high temperature like 400 to 500 degrees Celsius temperature and 150 to 300 atm pressure. Here is a key diagram of the nitrogen cycle. Its key components include nitrogen fixation, nitrification, assimilation, and denitrification. In nitrogen fixation, atmospheric nitrogen is converted into ammonia and ammonium. Nitrification, ammonia is converted into nitrites and then nitrates by nitrifying bacteria. In assimilation, plants and organisms take up nitrates for growth, and in denitrification, nitrates is converted back into atmospheric nitrogen by denitrifying bacteria. This cycle shows how nitrogen moves through the environment, making it available to living organisms. Key electrochemical pathways. The first one is the electrochemical nitrogen reduction reactions, NRR. The electrochemical reduction reaction is a process in which atmospheric nitrogen gas is directly converted into ammonia using electricity. This avoids the need for high temperatures and pressures and can be powered by renewable energy. Its mechanism includes N2 absorption, then activation, and then proton electron transfer. We will discuss its all the mechanisms one by one. N2 absorption. The nitrogen molecule attached to the surface of the catalyst because N2 has a strong triple bond. Absorption is essential for weakening and activation the molecule. Activation of the N2. The catalyst has breaker weakens the N triple bond and making nitrogen atom ready to participate in chemical reactions. In proton-electron transfer steps, electrons from the power source and protons from the electrolyte combines with the nitrogen step by step forming intermediate until ammonia is produced and released. The cathode materials which are used in NRR. Different types of catalyst like metal catalyst, single atom catalyst, and carbon based materials. There are three types of catalyst. First one is the transition metals like iron, molybdenum, ruthenium and gold. Single atom catalyst, individual metal atom anchored on a support material offer highly active selective sites that reduce energy loss and suppress unwanted side reactions. Single atom catalysts are the type of catalyst where isolated metal atoms are dispersed on a support material. They offer high catalytic activity, maximum atom efficiency, and tunable properties. But how it is possible that a single atom catalyst suppress the unwanted side reactions? Single atom catalyst suppresses unwanted side reaction by providing uniform active sites, reducing assemble effects, enhancing selectivity, and minimizing the multi-side interactions. Carbon-based materials, defect-rich carbon, doped graphene, and carbon nanotubes help support metal atoms and sometimes act as a catalyst. Defect-rich carbon, doped graphene, and carbon nanotubes can act as a catalyst due to edge defect and vacancies, doping-induced active sites, high surface area, and conductive properties. These materials influence both reaction speed and selectivity. It means that these materials fast or speed up the rate of the reaction, and reaction selectivity refers to the catalyst ability to favor the one reaction pathway over another, producing a specific product while minimizing the byproducts. There are several types: chemoselectivity, regioselectivity, and stereoselectivity. Now we study the challenges like lower selectivity and competing HER. Lower selectivity, only a small portion of the electrochemical energy actually produces ammonia. Much of it gets consumed in side reactions. In electrochemical nitrogen reduction, only a small portion of the electrochemical energy produces ammonia due to competing HER, low Faradic efficiency, high overpotential requirements, and catalyst limitations, mass transport limitations. But how electrical energy consumed in side reactions? In electrochemical nitrogen reduction, electrical energy is consumed in side reactions like hydrogen evaluation reaction, oxidation reduction reaction, and catalyst degradation or corrosion. These side reactions reduce the Faradic efficiency and overall efficiency of the ammonia production, wasting electrical energy. Bec- uh, and the second challenge is the competing HER. Water splitting often occur more easily than N2 reduction, leading to hydrogen gas instead of ammonia. HER reduces the efficiency of the NRR and makes it difficult to obtain high yields. Water splitting like H2O into H2 plus O2 occurs more easily than N2 reduction due to lower thermodynamic potential, 1.23 versus 1.45 for N2 reduction. Simpler reaction kinetics, abundant water molecule near a catalyst surface, and favorable absorption for H2O on catalyst surface. But how HER reduces the efficiency of the NRR and makes it difficult to obtain high yield? HER reduces NRR efficiency by competing for electrons and protons, blocking active sites on catalyst, producing H2 gas, reducing N2 availability, and increases energy losses. Because of these challenges, researchers focus on designing catalysts and electrolytes that favor NRR and suppress HER. The second pathway is the electrochemical nitrification. First one is the oxidation of NH3. Electrochemical nitrification is the process where ammonia is oxidized into nitrogen oxides such as nitric oxides, nitrogen dioxide, and nitrite ions. This reaction occurs at the anode where ammonia loses electrons and converted into more oxidized nitrogen species. The final product depends on the catalyst, electrolyte pH, and voltage applied. Here is a key diagram. This diagram illustrates the nitrogen cycle process of nitrification and denitrification. In nitrification, the ammonium is oxidized to nitrite by ammonium oxidizing bacteria AOB. Then nitrate by nitride oxidizing bacteria NOB. Requirement oxygen is needed. And in denitrification, NO3 minus. Nitrate is reduced to nitrogen through intermediate NO2 minus NO and N2O by heterotrophic bacteria HB. Carbon source is needed. Here are some anodic reactions and catalysts. At the anode, ammonia undergo multi-step oxidation. Like in these reactions, first reaction shows the stepwise decomposition of ammonia into nitrogen radical through intermediate radicals like NH2 radical, which is called aminoyl radical, and nitrene NH radical. These steps likely involve the loss of hydrogen atoms. In the second reaction, after forming nitrogen radical, the nitrogen can react with the oxygen under different conditions to form nitric oxide, nitrogen dioxide, and nitrate ions. Now, catalyst used for the anodic ammonium oxidation includes platinum, which is highly active but expensive, iridium oxide, and ruthenium oxide are stable and effective at high pressures. Nickel-based catalyst, lower cost, commonly used in alkaline media. These catalysts helps control reaction pathway and improve reaction efficiency. Here are some applications like in sensors. Electrochemical nitrification is used in ammonia sensing devices. Ammonia sensing devices are used to detect and measure ammonia concentration in various environments. First one is the oxidation current producing during NH3 into NOx conversion is proportional to ammonia concentration, useful in environmental monitoring, food safety, and industrial processes. Second one is the wastewater treatment. Electrochemical oxidation of ammonia helps remove nitrogen pollution from wastewater, convert harmful NH3 into nitrates or nitrogen oxides, reducing eutrophication risks in rivers and lakes. Eutrophication is a process where excess nutrients like nitrogen and phosphorus stimulate excessive algae growth in water bodies, leading to depleted oxygen, harmful algal blooms, death of aquatic life, and decreased water quality. It offers a clean, chemical-free method compared to the traditional biological nitrification. The third pathway is electrochemical denitrification, reduction of nitrate or nitrite into nitrogen gas. Electrochemical denitrification is the process in which nitrates and nitrites ion in water are reduced into harmless nitrogen gas using electricity. This reaction takes place at cathode where electrons are supplied to break down the nitrite step by step until the nitrogen gas is released. Here is a general reaction, and then we used for removing nitrate pollution from water. High nitrate level in water cause eutrophication, groundwater contamination, and death problems. Eutrophication, I explained it earlier, and then we explained the groundwater contamination occurs when polluters enters aquifers affecting water quality. Common contaminants include nitrates, heavy metals, industrial chemicals, and pathogens. Problems like methemoglobinemia. Methemoglobinemia is a condition where methemoglobin levels rises, reducing oxygen delivery to tissues. Causes includes nitrate and nitrite ingestion, certain medications, and genetic disorders. Electrochemical denitrification is used because it requires no chemicals, work at room temperature and moderate voltages, can be combined with renewable energy, produce environmentally safe nitrogen gas as the final product. It is an eco-friendly alternative to biological denitrification or electrochemical treatment methods. Here are some catalysts like copper, silver, and bimetallic catalyst. First one is the copper. Copper is highly selective for reducing nitrites to nitrogen gas. It is low cost and widely used. It works well in neutral and alkaline electrolytes. How copper works well in nitrogen and alkaline electrolytes? Due to high conductivity, stability, and resistance to corrosion, ability to facilitate electron transfer, and favorable interaction with reactors and intermediates. Second catalyst is the silver. It is efficient for converting nitrites to N2. It is stable and active at low overpotentials. It is useful in sensors and high preference reactors. How silver is useful in sensors and high performance reactors due to high electrical conductivity, excellent thermal conductivity, antimicrobial properties, and catalytic activity. In sensors, silver enable detection of biomolecules and gases. In reactors, silver catalyzed reactions like ethylene oxide production and fuel cells, enhancing efficiency and performance. Bimetallic catalyst, like in this process, two metals are combined with each other. It offers better selectivity and faster reduction. It improves the stability and reduces unwanted byproducts like ammonia formation. Bimetallic catalysts enhance stability and reduced unwanted reaction by modifying electronic properties, creating synergistic effect, altering surface structures, and improving reactant absorption. This leads to increased selectivity, reduced reactivation, enhanced activity, and minimized side reactions. Bimetallic catalysts are currently one of the most researched options due to tunable activity and efficiency. Tuning or tailoring of bimetallic catalysts to enhance their activity. Material and catalyst design. First is the metal catalyst. Metal catalysts play a central role in electrochemical nitrogen conversion because they help absorb, activate, and convert nitrogen containing molecules. Common metal catalyst includes iron, molybdenum, ruthenium, copper, silver, gold, and platinum. Iron, molybdenum, ruthenium for strong anti-activation ability, copper silver for excellent for nitrite reduction, and gold platinum highly active but expensive. These metals improves reaction speed, selectivity, and efficiency. Metal nitrogen carbon system. In this, metal atoms are embedded within the nitrogen doped carbon structure. Features includes it provides highly active metal nitrogen coordination sites. Metal nitrogen coordination sites are crucial in various catalytic reactions including NRR, nitrogen reduction reactions, oxygen reduction reactions, ORR, and carbon dioxide reduction. It offers large surface area and good conductivity. It improves selectivity by controlling how a nitrogen molecule binds to the catalyst. It improves selectivity by controlling how nitrogen molecule binds to the catalyst. The example iron nitrogen carbon system, cobalt nitrogen carbon system, and nickel carbon catalyst system. They are widely used for NRR, ORR, and denitrification like CO2 reduction. How metal carbon systems used for NRR, ORR, and denitrification? Because metal centers facilitate N2 reduction to ammonia, metal side enhances O2 reduction to H2O in ORR, and in denitrification metal centers reduces NO3 to N2. Transition metal nitrides and oxides. These materials combine metal with nitrogen or oxygen atom, giving them special properties. The first one is the metal nitride. Excellent electron conductivity and strong N2 binding ability useful for NRR and ammonia production. Metal oxides like titanium, ruthenium oxide and iridium oxide. Highly stable and active especially for ammonia oxidation, good for high voltage and harsh environment. Metal oxides are valuable for high voltage and harsh environments due to high stability, resistance to corrosion, wide band gap, and tunable properties. They are durable and effective for both oxidation and reduction reactions. Single atom catalyst. Single atom catalyst contain isolated metal atom anchored on a support such as carbon. Advantage high atomic efficiency, highly selective active site, and strong interaction with support materials. Common SACS single atom catalysts include iron single atom catalyst, molybdenum single atom catalyst, and ruthenium single atom catalyst. They are especially promising for NRR because they suppress unwanted hydrogen evaluation HER. Role of surface area, defect sites, and conductivity. First of all, we study about the surface area. High surface area, more reactive site, and faster reaction. Nanostructure materials such as nanotubes, nanosheets, and porous carbon improve nitrogen absorption. Defect sites such as vacancies, pores, or doped atoms help weakens the N-triple bond and increasing binding of nitrate or nitrides, and it improves the catalytic performance. Defects are often intentionally induced to enhance the activity. Third one is the conductivity. Good electrical conductivity ensures faster electron transfer in electrochemical reactions. Materials like carbon nanotubes, graphene, and metal nitrides provide excellent electron mobility, improving efficiency and lowering energy requirements. Now we will discuss the electrolytes and cell design. First one is the aqueous and non-aqueous electrolyte. Aqueous electrolyte. It uses the water-based solution such as acidic, neutral, or alkaline media. Advantage it is safe, cheap, and easy to handle. Good proton availability help ammonia formation. But its challenges it has very low solubility in water, so its reaction rates are very slow. Strongest H2 reaction H2 evaluation competes with nitrogen reduction. How H2 produced in HER? H2 is produced in hydrogen evaluation reaction through volcanic pathway and Hydrosky pathway. Catalysts like platinum, and nickel-based materials facilitates this process in enabling efficient H2 production. Non-aqueous electrolyte. It uses the organic solvents like acetonitrile, ionic liquids, and alcohols. Advantage is it has higher solubility, HER is suppressed, and improved selectivity for NRR. The challenges includes it is expensive, can be unstable, and harder to scale industrially. Non-aqueous electrolytes face industrial scaling challenges due to high cost, limited ionic conductivity, moisture sensitivity, and complex synthesis and purification. Proton sources and pH effect. pH strongly affects by selectivity between NRR and HER, proton availability, and catalyst stability. Acidic electrolytes has abundance of H plus ions. It increases the ammonia formation rates but also increases hydrogen evaluation, reducing efficiency. Hydrogen evaluation is a crucial process for clean energy production involving water splitting and proton reduction. Neutral and alkaline electrolytes. It has fewer protons, so HER suppressed in this process, better NR selectivity, but too few protons can limited ammonia formation. In proton transfer, we use water molecules, which are the proton donors, and membrane delivered proton in PEM membranes. How membranes improves the efficiency by controlling the ion flow. Membranes improve the efficiency by selectively allowing ions to pass through, blocking unwanted ions and molecules, and maintaining the concentration gradient, reducing electrolyte polarization. Here are the membranes like PEM and AEM, proton exchange membrane and anion exchange proton. PAM allows H plus ions to move from anode to cathode, good for ammonia synthesis, controls where protons go, improving selectivity and keeps products separated. M for the hydroxyls, useful for denitrification and it suppresses the HER. And we earlier describes why membranes improves the efficiency by controlling the ions flow. Membrane improves the production, separation, selectivity, and efficiency by controlling ion flow. Reactor configuration, first one is the flow cell. Electrolytes and gases continuously flow through the cell. High mass transport of N2, better reaction sites, industrially relevant, often used with gas diffusion electrodes. Flow cells with gas diffusion electrode enhances performance by facilitating gas transport to reaction sites, increasing reactant availability, improving mass transport, and reducing diffusion limitations. Solid state cells use solid electrolytes like ceramic oxide, often operated at high temperatures, high efficiency, and high H2 activation used in solid oxide electrolysis systems. Solid state cells operate at high temperature due to improved ionic conductivity, enhanced electrode kinetics, and reduced interference resistance. Here is a summary of aqueous, non-aqueous pH, membrane flow rate, and solid state cells. Aqueous electrolytes are cheaper but low N2 stability and it is used for HER. Non-aqueous better for N2 solubility and it has better selectivity but it's most costly. pH control the proton availability and HER competition. Membrane guides the ion movement and improves selectivity. Flow cells are highly productive and scalable. Solid state cells are requires high temperature efficient for N2 activation. Here are the applications of the electrochemical nitrogen cycle. The first one is the sustainable ammonia synthesis, which is also called green fertilizers. Electrochemical methods can convert N2 into NH3 using renewable energy. Unlike the Hammad-Bosch process, these chemical systems operate at low temperature and pressure and emit near zero carbon dioxide. The produced ammonia can be used to make fertilizer without fossil fuels, ideal for small-scale decentralized ammonia production, for example, farms producing their own fertilizers. The Haber-Bosch process can achieve near zero carbon dioxide emission when powered by renewable energy, solar and wind energy, using green hydrogen from water electrolysis, and implementing carbon capture and utilization. Decentralized ammonia production offers localized supply chains, reduced transportation cost, increased energy efficiency, and enhanced energy security. Farms producing their own fertilizers can benefit from localized production, reduced transportation cost, tailored nutrient blends, increased crop yields, and improved soil health. Wastewater nitrate removal. Many water sources contain excess nitrate from fertilizer and industrial waste. Electrochemical denitrification converts nitrate back to the N2 gas, safely returning nitrogen to the atmosphere. Benefits: no need for added chemicals, can be installed in wastewater treatment plants, work on industrial effluent, drinking water, and agricultural runoff. Nitrogen removal from wastewater, drinking water, and agricultural runoff involves biological denitrification, ion exchange, reverse osmosis, and electrochemical reduction. Distributed and localized nitrogen fixation for agriculture. Instead of transporting ammonia long distances, small electrochemical units can be placed like farms, remote villages, and at fertilizer distribution centers. Remote villages often face challenges like limited access to clean water, inadequate sanitation, energy scarcity, limited healthcare and education. This allows on-site production of ammonia or nitrogen fertilizer. The advantages includes transportation, it reduces the transportation and storage cost, helps regions without large industrial infrastructures, it supports the precision agricultural produced only when it is needed. Energy storage. Ammonia can store renewable energy in chemical forms. It can be cracked back into hydrogen for fuel cells, burned in energies or turbines, used directly in solid oxide fuel cells. Electrochemical nitrogen reduction allows production of ammonia using excess renewable energy, helping balance the power grid. Electrochemical conversion of wastewater compounds can be produced ammonia for fertilizer, nitric acid for chemicals, urea for agriculture, and hydrogen for fuels. Artificial nitrogen cycle in industry. Industries can create closed loop nitrogen system. Waste nitrogen compounds can be electrochemically converted back into the useful products. This reduces pollution and closes the nitrogen loop. Here are some applications which includes the chemical manufacturing, fertilizer plants, food processing industries, power plants. Such systems help achieve circular nitrogen management, reducing environmental impact. Now we will discuss the advantages of the electrochemical nitrogen cycle. The first one, it requires low temperature and low pressure. Unlike the Haber-Bosch process, electrochemical conversion works at near ambient conditions. This reduces energy efficiency, cost of equipment, and safety risks. It allows operation in smaller and localized reactors. The second one is the use of renewable energy, like energy from sun is solar, energy from wind is the wind energy, energy from water is hydro energy, and energy from earth is called the geothermal energy. This eliminates dependence on natural gas and fossil fuels. It renewable powered and to conversion enables green ammonia and sustainable nitrogen management. Third one is the reduced carbon footprint compared to the Haber-Bosch process. Traditional Haber-Bosch emits carbon dioxide because it relies on high temperature pressure and natural gas reforming to produce hydrogen. The traditional Haber-Bosch process is produce ammonia from N2 and H2. It requires high pressure and high temperature. It uses the iron-based catalyst and it consumes the 1 to 2% of the global energy and emits significant CO2. Electrochemical processes emit almost zero carbon dioxide, do not require fossil fuel derived hydrogen, can even integrate with carbon neutral energy systems. Overall, they drastically lower greenhouse gas emission. Fourth advantage is the modular and scalable system. Electrochemical reactors can be small, medium, and large. Modular design means it is easy for installation, simple scaling by adding more units, and it is distributed for ammonia production. This flexibility is impossible with the massive centralized Haber-Bosch plants. Cell design for the standardized measurements involves defined geometry. Challenges and limitations: low efficiency and selectivity. Electrochemical nitrogen system currently converted only a small fraction of input energy into output like ammonia. Many electrons are wasted inside reactions. Selectivity towards nitrogen reduction is often low because N2 molecules is very stable. It has very strongest triple bond. Poor solubility in aqueous solutions. Nitrogen gas dissolves very poorly in water, much lower than gases like CO2. This limits the amount of N2 available at the catalyst surface. It has low solubility, its mean reaction rate is very low, and ammonia yield also low. Researchers try to solve this using gas diffusion electrode, flow cells, and non-aqueous electrode with higher N2 solubility. Here is a competition of the electrochemical nitrogen cycle or NRR with the HER. The HE process occurs very easily in water-based systems. HER is faster and more favorable than NRR. As a result, most electrons make hydrogen, not ammonia. It increases the efficiency and selectivity, which is dropped significantly during this process. Designing catalyst that suppresses HER while activating N2 is one of the biggest challenge. Catalyst stability issues like it degrades due to corrosion, structural changes, and loss of active sites. Catalyst poisoning, its mean the impurities are binding to the active sites and poison it. Unstable catalysts give poor long-term performance. This makes scaling to industrial levels difficult since real systems must run for months or years continuously. Need for standardized measurement protocols like different research groups used. The first one is the electrolytes. For standardized measurements, electrodes are chosen based on stability, conductivity, pH range, and compatibility. Cell design for standardized measurements involves defined geometry, controlled temperature, precise electrode placement, and minimized junction potentials. Analytic methods for these standardized measurements include potentiometry, volumetry, colorimetry, impedance spectroscopy. Calibration techniques include external standardization, internal standardization, standard addition, and calibration curves. This leads to inconsistent data and sometimes overestimated ammonia yield. Inconsistent data can arise from instrumental errors, human mistakes, environmental factors, and methodological flaws. Without standard protocols, comparing results across studies is unreliable. International standardization is needed to judge real process in the field. Here are some research trends. The first one is the development of highly selective catalyst, which favors the NRR and suppress the HER. Scientists are developing single atom catalyst, metal nitrogen carbon materials, bimetallic catalyst, and rich defect rich carbon structures. These catalysts offer end-to absorption and stronger activation of the N triple bond and improved electron transfer. Mechanistic studies using in situ spectroscopy. Researchers are increasingly using in situ and operando analytical tools to observe reactions as they happen in real time. In situ Raman spectroscopy provides real-time molecular insights. X-ray absorption spectroscopy probes local atomic structures and element specifics. Infrared spectroscopy identifies the molecular vibrations and it is non-destructive. Electrochemical mass spectroscopy couples electrochemistry with MS detection and it is used for the real-time analysis of electrochemical reactions. These studies help scientists understand how and to bind to the catalyst, whether reaction steps are associative or dissociative, how intermediates form and convert, why HER occurs, and how to suppress it. Mechanistic insight is better catalyst design. Optimization of the electrode and cell architecture. Electrolyte composition significantly affects atom solubility, proton availability, and selectivity. Research focus on high solubility electrolytes like ionic, liquid, and organic solvents. Buffer system that balance protons and HER suppression. Buffer system offer flexible food services, variety of options, and efficient surfaces, and it is suitable for large groups. Additives that stabilize reaction intermediates. Additives can enhance food products by improving texture, extending shelf life, enhancing flavor, and boosting nutrition. Cell design improvements includes flow reactors for high gas transport, gas diffusion electrode, and membrane-based systems. These advancements increases ammonia production rates and reduces energy losses. Fourth one is the integration with the renewable energy. Many research groups test electrochemical nitrogen system with solar panels, wind turbines, and photocatalytic devices, making green ammonia. Green ammonia is produced using renewable energy, reducing CO2 emission. It is sustainable fuel and fertilizer with applications in carbon-free energy storage, transportation, agriculture, and industry. Produced via electrolysis or Hammad wash process with renewable energy, green ammonia supports a low-carbon future. The second goal is matching ammonia production to variable power supply, intermittent energy, creating decentralized micro-fertilizer plants. Decentralized micro-fertilizer plants localize production, reduce transportation cost, customize fertilization, sustainable production, and increase food security using renewable energy and modular technologies. Researchers also explore hybrid systems combining electrochemical plus photoelectrochemical processes. Fifth one is the DFT. DFT play a major role in guiding experiments. DFT helps in predicting how catalyst interacts with the N2, identify active sites, model reaction pathways, and energy barriers. Screen thousands of catalyst candidates before synthesis. Machine learning plus DFT accelerate discovery of high-performing catalysts and new materials. Now we will discuss the future prospects. First one is the commercial scale electrochemical ammonia plants. In the future, large industrial facilities facilities may produce ammonia using electrochemical reactors powered by renewable electricity. This operates at low temperature, pressure, low carbon emission, and higher flexibility to respond to challenging power supply. This would allow industries and countries to move away from the traditional carbon intensive Haber Bosch process. The second one is the on-farm small-scale ammonia production. The electrochemical system can be built as compact modular devices, making ammonia production possible directly at farms. Its benefits include farmers can produce fertilizers on-site, reducing transportation costs, ideal for remote and developing regions, support precision farming, fertilizers is produced exactly when needed. This decentralization increases food security and reduces environmental impact. Third one is the circular nitrogen economy in wastewater systems. Wastewater contains high level of nitrogen species. Future electrochemical technologies could recover nitrogen from wastewater and convert it into useful products like ammonia or nitrogen gas. This creates circular nitrogen economy. Circular nitrogen economy aims to minimize nitrogen waste, optimize nitrogen use, promote sustainable agriculture, and reduce environmental impact. Strategies includes recycling, efficient fertilizer use, and innovative technologies supporting a more sustainable food systems. Such systems could be integrated into municipal wastewater plants or industrial facilities. Fourth one is the potential for carbon neutral or carbon negative nitrogen chemistry. By using renewable energy or new renewable electricity and avoiding fossil fuel derived hydrogen, electrochemical nitrogen processes can become carbon neutral. In some cases, they may even be carbon negative. For example, when coupled with carbon capture, used with biomass derived electricity applied to reduce nitrogen pollution while generating useful products. This opens the possibility of a future where ammonia and other nitrogen compounds are produced with zero net greenhouse gas emissions. Now we will conclude it. The electrochemical nitrogen cycle plays a crucial role in sustainable chemistry because it enables nitrogen conversion using renewable electricity, low temperature, low pressure. This makes it far cleaner and more environmental friendly than traditional nitrogen processes. These electrochemical methods have the potential to replace or complementing existing nitrogen industries such as Haber-Bosch process and conventional wastewater treatment by offering decentralized, flexible and low-carbon alternatives for ammonia production and nitrogen management. However, continued progress is essential. Improvements in catalyst design, reaction selectivity, system efficiency, and long-term stability are needed before large-scale applications become practical. Ongoing research in materials development, mechanistic understanding, and reactor optimization will drive the technology forward. It means that we convert in electrochemical nitrogen conversion, we convert the other forms of the nitrogen into the atmospheric nitrogen by using different steps, by different processes, but more efficiently with the help of lower temperature, lower pressure, and it is eco-friendly system than traditional, which makes or which emits a very large amount of carbon dioxide in the environment and pollute the ecosystem. So the renewable electricity reduces its risks and it is eco-friendly. So, by developing in mechanistic understanding and reactor optimization, this technology, this process, and this method is derived further processes, and I hope so you all understand all the features of this process and um, that's all about my presentation. Thanks for watching my video. Thank you so much.